All right, we have been talking about variance, and what it basically means is we want our estimator to be precise. So if we have a population, we take a sample from it, and then based on that sample, we estimate the population average. We want a value that results to be as close as possible to the true value. But that's actually not really variance. That is mean square error, because variance says how much does my particular sample take. So the value that follows from my sample, how much does it deviate from the average of all possible samples? Now that's good to know, but just imagine that the average of all possible samples is actually not equal to the true value. So I could then have the following relationship. There is the average estimated from my sample. There is the average across all samples, the average of the averages across all samples, and there is the population average. So, well, I'm writing it down now. I'm drawing it for an average. The calculations that you find on the slide are actually for the total, but it's exactly the same thing here. So there are these two sources of discrepancy. A systematic difference here, which is the bias, and then a random sampling-based one, which is based on sample-to-sample variability. So it can be shown that the typical square deviation, and that's this guy, from what I get from my sample and what is the true population value is actually decomposable into two parts that come down to the variance plus the square of the bias. So what does it matter to have a very precise quantity but with a huge bias? I'm still nowhere. I would think that I'm doing well, but I'm still far away from the population quantity. Likewise, I can have a very, very, very small bias or an unbiased quantity, and many people say we want the quantities to be unbiased, we want the estimators to be unbiased, but if there is a huge variability, I'm nowhere. So we really need to think of a good balance between the two, and that is the mean square error. Okay, variance is easier to study because the algebra just lends itself more naturally to studying that. But bias, on the other hand, depends on sources that are very hard to quantify, like discrepancies between the sample frame and the population. They're much more difficult to grasp, but nevertheless they are there. So they should definitely not be ignored. We should do everything we can by really carefully reflecting upon our population to reduce or at least avoid bias. So here is survey town again, with X the number of lots and Y the number of buildings on those lots per block, with the totals and the averages. Nothing special here, we've actually seen that already before. And then the corresponding population variances can be calculated. For X and for Y, they're different as we said before. That doesn't mean one is better than the other, because here we're talking about two different quantities, X and Y. The population total for X and for Y cannot be directly compared. They're different quantities, they're different estimates. But now, let me go to sampling without replacement and samples of size 1. Of course, I can also do with replacement, because with size 1 there is no replacement possible whatsoever. There are 8 possibilities, so these are the 8 possible samples of size 1 out of survey town, with, for example, the estimated totals here, of which the average is 36, unbiased. The variance is, I average the square deviation and I get 336, with a standard error of 18, which is a square root. And then I do sampling with replacement still, but of units that, or samples that consist of two members of the population, 1 and 2, 1 and 3, 1 and 4. They all have the same probability because there are 28 different ones. It continues on the next page. We can calculate the averages, and then we look at the average here, and we find a variance of 144. Now 144 is smaller than 336, We know that both are unbiased. We actually verified that because twice do we get the average 36. So we say sampling without replacement is more precise in samples of size 2 than in samples of size 1. And the mean square error is smaller indeed. But now, let's say we make a mistake and for some reason somebody omitted by accident number 8 from the population. So we no longer know about number 8. Well, then of course we're going to have 7 choose 2 is 21 different samples. Every sample that contains the number 8 is removed. 21 only, of which the average is 28 rather than 36. There is bias. If we calculate the variance, it looks smaller than before. So you would say this is better. But no, we have to add the bias square and we find 145.67. So there is a little bit of bias, but the mean square error really has not changed all that much. And the RMSE, the root mean square error, is a more honest quantity now than the standard error. The standard error is based on one source of discrepancy, namely variability. But the root mean square error also on bias. And that is a different thing. Okay, that brings me to the end, not only of chapter 3, but also the first introductory part. And believe it or not, in part 2, we will move into simple random sampling. Didn't we do that then? Yes, we did look at simple random sampling, but only from the perspective of, okay, from a bird's eye perspective, we look at our population from above and we can take all possible samples. The goal in the next part and part following will be, yeah, but what do I do if I only have a single sample to my disposition? What do I do then?